So in this section, we'll be talking about vertical motion and free fall. So mostly in the last problems, we've been talking about sort of cars, horizontal motion on flat surfaces. In this section, we're looking at, we're just changing the direction. It's going to be up and down motion. Free fall is if I take a ball and throw it up in the air, it's in free fall the instant it's left my hand. We make a few approximations with that. We assume that gravity is uniform and that there's no air resistance and stuff like that. But it works pretty good, even with those approximations. We pick the y-axis pointing positive, pointing down. That's a little unusual, and I wouldn't do that in a physics class, but it makes it a little easier if you're just dropping things to not have to deal with negative numbers. So neglecting air resistance, any object near Earth's surface accelerates downward at 9.8 meters per second squared, whether it's a pebble or a boulder or an elephant. It took us a long time as humans to sort of figure that out. Galileo showed everything pretty much falls at the same rate until you start including things like air resistance. A big boulder and a little boulder, when dropped off the Leaning Tower of Pisa, hit the ground at roughly the same time. It was one of the bones he had to pick with the ancient Greeks, who would argue that if something was 10 times heavier, it would fall 10 times faster. You can try it in your apartment or your house. It's clearly not true. So everything falls at about the same acceleration. It's 9.8 meters per second squared. We round that up to 10 for the purposes of our class because it's easier to multiply by 10 than 9.8, and it's only a 2% difference. So we can use our equations in the vertical direction, and they're the same equations we had from before. If a final velocity is equal to the initial velocity plus the acceleration times the change in time. This just came from the rearrangement of the definition of the acceleration, which said the acceleration is the change in velocity over the change in time. If we use g for the acceleration, this is our vertical motion problem, then we replace the a with the g, and then the g is just 10 meters per second squared, and so our final velocity is the initial velocity plus 10 meters per second squared times however long it's fallen. All right, so what does that do? Let's look at that for a second. We say a ball is dropped from a bridge. What's its velocity 2 seconds later? Right? Well, we could ask the first question and say, well, what's its velocity the instant it's dropped? And it turns out that's 0. If you throw it down, it has a velocity when it left your hand that's higher than 0. But if you just let go of it, the instant it's let go, it's starting from rest. And so we're always interested in what happens after it's been released. These equations apply to what gravity does to it, not what your hand does to it. And so we take your hand's action into account in the initial velocity. If you threw it, it might have a v1 equal to something that's not 0. If you dropped it, it's 0. And so since the ball was dropped, we have v1 equals 0. And t is, and we want to know what's happening 2 seconds later, so our t is 2 seconds. Right? That t is the same thing we've been calling delta t, or t2 minus t1. So it's just fallen for 2 seconds. So once again, we get v2 equals v1 plus a2. This a is just the acceleration of gravity, and so that's just the 10 meters per second squared. So I get v1 plus 10 meters per second squared times the time. v1 is 0 because it was dropped. We already talked about that. The time is 2 seconds, and so the final velocity is 20 meters per second. In fact, you can just look at this equation here, this middle one, v1 plus 10 meters per second squared times time, and say that any object that's dropped from rest will have a 0 here. You'll just get 10 meters per second squared times how long it's fallen. So if it was 1 second, after 1 second it would be going at 10 meters per second. After 2 seconds, 20 like we got. On the next line you can see after 3 seconds it's 30, after 4 seconds it's 40, and so on. So we could say, look, if the ball hits the water below the bridge 4 seconds later, how fast was it going when it hit the water? Well, 10 meters per second for every second, and so it's 40 meters per second. Right? I've worked it out here. And so we can ask the question, well, the ball drops from the bridge, it falls for 4 seconds. How high is the bridge? And so now we can go back and look at our average velocity equation. The average velocity for the ball that was dropped is just its initial velocity, which was 0, plus its final velocity, which was 40. Oops, I have a little typo there. And so that should be a second there. But anyway, it's 40 plus 0 divided by 2, which is 20. And this should make sense because the ball started its journey at 0 meters per second because it was dropped from rest, and right before it hit the water, it's doing 40. And so its average is 20. And then we can go back to our equation for the average velocity, which is the average velocity is the change in position over the change in time, or the change in position is the average velocity times the time. Since we know the average velocity is 20 meters per second, and it fell for 4 seconds, the change in position is the average velocity times the change in time, or 20 meters per second, times 4 seconds, which is 80 meters. So that tells me how high my bridge was. We could solve this a different way using the other equation that we came up with in the Kinematics 3 section. We could use the d is equal to v1 times t plus 1/2 times the acceleration times t squared. Once again, v1 is the initial velocity. Well, that was 0. And so 0 times anything is 0, so this term just goes away. And we get, and once again, our acceleration is just g, so that's just the 10 meters per second squared, and the time is how long it fell, which is 4 seconds. And so we plug that in down here. We say the distance is equal to 0 times 4 seconds. That's the first term here, plus 1/2 times 10 meters per second squared times 4 seconds squared, because that's what the t squared is. Right, 4 squared is 16. 16 times 10 is 160, divided by 2 is 80. This is the same 80 that we got on the previous slide, solving it the other way. So the height of the bridge shouldn't depend on how you calculate it. As long as you calculate it correctly, we get the same answer using both of these techniques. So now we can ask a few questions, and I can just say, well, suppose the ball was thrown downward instead of just dropped. What's its velocity 2 seconds later? Well, if it was released at 10 meters per second, right? So let's switch to the other slides like this. I can say, look, v2 is equal to v1 plus the acceleration times the time, right? And that's just 10 meters per second plus 10 meters per second squared times, we wanted to know what its velocity was 2 seconds later, right? So times 2 seconds, which is, so 10 times 2 is 20, plus 10 is 30 meters per second. Right. Similarly, I can say, what is its velocity 6 seconds later, right? I can say v2 is equal to v1 plus the acceleration times the time. That's equal to, once again, 10 meters per second, because it was thrown down, plus 10 meters per second squared times 6 seconds. 10 times 6 is 60, plus 10 is 70. 70 meters per second. So now in the next question, I say, well, suppose the ball was thrown upward at 10 meters per second, right? And so I can say, so let me just switch back for a second and let you read that. Oops. There we go. In the next question, I say the ball is thrown upward at 10 meters per second. What is its velocity 1 second later, 2 seconds later, 6 seconds later, right? And so if I come back over here, so in this case, v1, if it's thrown upwards at 10 meters per second, its initial velocity is minus 10 meters per second. Are you with me? Because I said down is positive, so that means up is negative. And so my equation would look like this. It was v2 is equal to minus 10 meters per second plus 10 meters per second squared times 1 second, right? And so 1 second later, its velocity is 0 meters per second. What does that mean? If I threw it up, what has happened 1 second later? So then you should be able to calculate what its velocity is 2 seconds later or 6 seconds later. Let's go to the next one. Suppose a ball is thrown upward at 40 meters per second. How long does it take to reach its highest point? Right? Right, and so if I throw a ball up, let's go back to this slide here. Right? If I throw a ball up like this, it eventually comes back down, right? And so what can you say about this point here? Well, if you think about it, if I throw a ball upward, its velocity here at that point is 0, right? It starts out going up at 40 meters per second, so I get v1 is equal to 40 meters per second, right? But its final velocity is 0, so I can say, look, v2 is equal to v1 plus the acceleration times the time, right? But at the top, v2 is equal to 0. So I can just say 0 is equal to v1 plus the acceleration times the time. Or I can say, if I rearrange this, I can say the time is equal to minus v1, because I have to subtract v1 from both sides. So if I was going to solve this, I would say minus v1. I'm going to solve for the time. So it's minus v1 equals the acceleration times the time. And then I can say the time is equal to minus v1 over the acceleration, and that's minus 40 meters per second over 10 meters per second squared, right? One of the minus signs comes from the fact that I subtracted v1, and one of the minus signs comes from the fact that the ball was thrown upward. Here v1, sorry, it should be minus 40 meters per second, right? Because it was thrown upward and down is positive. And so this is 4 seconds. So it takes 4 seconds to reach its highest point. The key to this one is sort of recognizing that it's at its highest point, that's when its velocity is 0. That's the thing we're calling v2. And we're looking for the time for that. And so that's what we calculated.